our sense of smell is remarkable and quite different from our other senses of sight and hearing. Among the thousands of scents that we can recognize, many of them may well trigger very powerful memories and emotions. It's as though our sense of smell is wired directly to our inner consciousness. It's also different in another way. The other senses of sight and hearing rely on us detecting waves, light and sound. But our sense of smell involves detecting particles, chemical molecules. Recently, scientists have begun to realize that when it comes to our sense of smell, something very mysterious is going on. For decades, biologists thought they knew exactly how our noses sniffed out different chemicals. But physicists like Jenny Brooks think there could be a new ingredient in the mix. And it smells like quantum mechanics.
A lot of people speak of the sense of smell and olfaction and science of olfaction as being a problem that's been solved, and we know all about it. And we do know a lot about it. We know about the ingredients, we know about the equipment that we use to smell. But I would argue that there's a little bit more to understand.
To understand more, I need someone to help me with a smell test. And Jem is going to sniff him out. Every human being gives off a cocktail of chemicals. Jem's nose could detect a single gram of it dissolved over an entire city. So she has no trouble finding the man I'm looking for. Meet Colin the gardener, a man who's used to smelling the flowers. Right then, Colin, I'm going to put your sniffing skills to the test. Cool. I've got a selection of chemicals here, and I want you to tell me what they remind you of. Okay. I'll start yours easily.
Oh, that's like a minty vapor rub.
It is, yeah.
Sort of thing, like, yeah. Sort of what you menthol. Yeah. But it's that essence.
Right, here's the next one. You should be able to recognise this one.
That's baking with my daughter. Icing sugar, sort of thing. Vanilla, yeah.
When our noses detect a chemical, they fire a nerve signal to our brains. But different chemicals create different sensations. The standard explanation for this is to do with the shape of the molecules. The conventional theory that goes back to the 1950s says that the scent molecule has a particular shape that allows it to fit into the receptor molecules in our nose. If it has the right shape, it's like a hand in a glove or a key in a lock. In fact, it's called the lock and key mechanism. With the wrong shape, it won't fit into the receptor. But with the right shape, it fits into the receptor, triggering that unique smell sensation. Different receptors are wired to different parts of our brains. So, when a menthol molecule locks into its specific receptor, it triggers that minty, fresh sensation. But the lock and key theory has always had a problem. And Colin's next test will show you why. Okay, how about this one? Quite a strong smell.
Oh, that's yeah.
What does it remind you of? What does it conjure up? What memories?
I think Christmas cake.
Yeah. Marzipan.
Yeah, that's it. Yeah.
It's almonds.
Very, yeah.
Colin identified the smell of marzipan or almonds. In fact, it's due to a scent molecule called benzaldehyde. What I didn't give him to smell was this other chemical, cyanide. Both benzaldehyde and cyanide have the same smell. They both smell of almonds. But these molecules are both very different shapes. So the lock and key mechanism as an explanation for how we smell can't be the whole story. So why would two molecules with different shapes smell the same? Quantum biology has a head-spinning explanation. It says our noses aren't smelling chemical molecules. They're listening to them. It's not just the shape of a scent molecule that matters. Let's take a closer look at this model of a cyanide molecule. The white ball here is a hydrogen atom, and the grey sticks are the bonds that hold it together with the carbon and nitrogen. But the reality isn't as simple as that. I can give you a better sense of what's going on if we look at this larger white ball. You see, atoms don't just sit still. The bonds that hold them together are like vibrating strings. And that gives us a whole new way of thinking about smell. The bizarre new quantum theory of smell is all about vibrating bonds. Chemical molecules are playing music for our noses. Imagine a receptor molecule in my nose is like my guitar. Before it can make a sound, a scent molecule has to enter my nose, and when that scent molecule is in place, its chemical bonds provide the strings, and it's ready to be played. The receptor molecules contain quantum particles, electrons. As they leap from one atom to another, they vibrate the bonds of the scent molecule, like my fingers plucking a guitar string. What's remarkable about this theory is that it tells us our sense of smell is about the vibrations of molecules, or wave-like behavior, and not so much about the shape of a particular scent molecule. Our sense of smell may be much more like our sense of hearing. A particular molecule, say that of grass, will vibrate at a particular frequency. But a different molecule, say that of mint, will vibrate at a different frequency. This would explain why cyanide smells like almonds. The two molecules have different shapes, but their chemical bonds just happen to vibrate at the same frequency.
The quantum vibration in the odorant is almost literally like a particle of sound. So yeah, we're saying that the process of smell could be exactly like an acoustic resonance event. It could be very analogous to hearing and seeing, actually.
But can we really be listening with our noses? A bizarre theory needs a bizarre experiment to test it. Here's how it works. This molecule has a musky aroma, like perfume. But if the theory is right, then I should be able to change its smell by changing its vibrations. The musky molecule contains lots of hydrogen atoms like this bonded to carbon atoms. But what if I were to replace all these atoms with a different form of hydrogen called deuterium? Now, it won't change the shape of the molecule, but it will change the way it vibrates. And here's why. Deuterium is twice as heavy as normal hydrogen, and so it vibrates more slowly. Now, different vibrations mean different smells. So if I were to make a new form of this chemical, all packed with deuterium atoms instead of normal hydrogen, it should smell different. Quantum biologists found a unique way to carry out this experiment. A smell comparison using the most sensitive noses they could find. Fruit flies. First, the flies were trained to avoid the modified version of the musky molecule. To be honest, I haven't got a clue how you go about training a fruit fly, but apparently you can. In the laboratory, the flies had to pass through a kind of maze. They were then given a choice. Go right for the nice musky smell, or left for the nasty modified version. They could definitely smell the difference. They always preferred the original and turned right. The fruit fly experiment gives hard evidence that quantum smell theory really works. But ultimately, it works in harmony with the lock and key theory. First, the scent molecule fits into the receptor. Then those molecular vibrations take over. Incredible as it seems, flies, humans and dogs may be smelling the sound of quantum biology. Our sense of smell is fascinating and mysterious as it is, but to think that when I encounter a particular scent and that sets off a whole wave of memories and emotions in my mind, that it's underpinned, that it's triggered by quantum mechanics, I think makes it even more remarkable.